Hi, this is Prem from Bennett University, second year, fourth semester. So today in this video, I'm gonna teach you graph traversal, breadth first search and depth first search. These are very important algorithms as they help you in graph traversals, and these are the first major stepping stone into the graph theory. As we move on further into the graph theory, we'll see more about the same algorithms implemented in different ways. As you know, graph are not like simple linked lists so that you can go in many directions rather than only two. So from forward and backwards. So these are gonna be interesting to learn, and let's see what we have here to offer. So let's see what are graph traversals. We have two main graph traversals, breadth first search and depth first search. So why do we need these special algorithms? So we can see that graphs are not like any other data structure. They have multiple points that one can go from one source to another. Like let's see, if we start from S, we can go to C or G. Which we go to first? It depends. If we can go to C, S, C, E, G, H and G, or we can go to S, C, G and then F. So it becomes really tough, and we need some methods to make it easy for us to transfer the graph and make it so that it is generalized. So then these two algorithms came in the way, breadth first search and depth first search. Breadth first search, we can see that what does breadth first search mean? From the name we can imply that it first searches its breadth. Breadth means its first children. Like if we are starting from node A, we can see that it will first go check out node S and then node B, and then it will go and see the children of node S, G, F, C, and then it will go to G and check out its children. This is how breadth first search works. And with depth first search, it will straight away go into the depth. So it will start from A and it will go into the depth of A, is like A to S and then S to G and then G to H and then G to H to E and H to C and then H to D, until and unless it finds an ending, it will keep on going. So how do we do these traversals? So for the basis of this, let's try to learn it with a simple approach and then we can make it generalized. So let's generalize it with let's take a data structure for BFS. We can say we have a data structure that allows us to make it enter from the back and make it come out from the start. Enter, out. And for depth first search, it is enter and out, both from the same source. Let me tell you why we take this approach. For breadth first search, let's take an example. Let's see for A. A will go, what are the, we will first check out A, and then what are childrens of A? They are S and B. So first we will add A and then we will check out its children. And then when we check out S and B, we will check out S's children. So if we remove S, then we can check out its children later on. For while as in depth first search, if we check out A, then we have to check out S and then we'll have to check out S's children. Now let's go into the depth of each algorithm and see how it works out. So let's first start with breadth first search. So our starting node will be A and we have to transverse this graph. So we enter A and then A gets popped out. We have gone through A. Let's write it down here. A. And then what are the childrens of A? We see S is there and B is there. So they enter from the back. And now we can see, first we check out S. Okay, we see that we have seen S. So we mark S here and pop it out. And for S, we see what are the childrens of S. We can see S has children such as G and C. So G and C will come from the back. So G came here and then C came here. Now we can clearly see we'll first check out B rather than G. So we will now check out B, and B will come here. B has any children? No, so nothing will be added at the back. And then now we can start with G. Now let's see what exactly happens in depth first search. Still here, we are going to complete it later on, but let's make a clear differentiation here on out so we don't have any issues later on. So we are starting with A. So A goes in, we have checked out A, and then A pops out. What are children of A? A has children B, B goes in, and on top of B goes S. Right, let me write it like a stack, it would be much better. So B goes in, and on top of B goes S. Now S pops out, we have checked out S, so we write down S here. And then what are the children of S? They are C and G. So you can see when we pop out the top, we will first check out its children, we will come at the end. So with a simple approach, you can learn that breadth first search, we enter at the back and come out at the start. And in depth first search, we enter at the start and come out from the start also, from one end. So what we can see that this is like a queue data structure that you must have studied about, and this is like a stack. So now let's write the full traversals using these two approaches. So for breadth first search, we came till G. So now we'll check out G. We'll pop it out and write down G. Now for G, what are the children of G? We can see there is H and there is F. So we'll write them at the back, H and F. Now for C, let's see what are the children of C. So we can see C is connected to F, E and D. As we have visited F, we won't be visiting it again. So we'll ignore it. In the pseudocode, I'll tell you how to do that. We basically maintain a simple visited array that checks out if something has been visited or not. Okay. So now let's go here and add these two. So C will get popped out, and we can write down C over here. And then what are the children? F we have already taken, C4 we will ignore it, we'll write down E, and then we'll write down D. Now H pops out. Does H have any? It is connected to E. We have already taken E, so we'll ignore it. So we write down H, and the same happens with F. F, all its children are connected, so we'll write down F. And then with E also has the same story, then E, and then D also, all these children are connected. So here we go, this will be our breadth first traversal. Let me write it down up clearly. A, S, B, G, C, H, F, E, D. So now let's see what our depth first search traversal looks like. As we know, we are going to use stack. I generally look at stack as a vertical data structure. It makes it more convenient to add more stuff to the top. So let's start with that. So we have already gone with A and S. Right, let's start from the start, right? I have of course made a hodgepodge over here. So we check out A. So we add A to the stack. Now that we have added it, let's see what all children it has. It has S and B. So we'll write down B and then we'll write down S while popping A out. When we pop out, it means that we have seen it. So we have seen A now. And then what is at the top? It is at the top, S is there. So we'll pop out S. See, when you pop out, then only you can add its children. You will see it clearly in the pseudocode that we are going to discuss later on. So S. We checked out S, and what are children of S? S is connected to G and C. So let's write these down, C and G. So now G pops out, and what is G connected to? G is connected to F and H. So it would be H and F. Now F pops out. So, and what is F connected to now? Now we can see that F is connected to C. So, but we have already visited C over here, so we are not gonna write that. So let's ignore that for now. And so there's nothing else that S is connected to that we haven't seen yet. So now let's go to H. We go to H and see what is connected to. It is connected to E, so we'll pop it out and we'll add an E to the top of our stack. Now E is also connected to C, so we'll pop that out and we will visit C later on. And now we'll visit C. Now C is connected to D, so we'll add D to the top of our stack. Now D gets popped out, D is connected to nothing, and then B gets popped out finally. So this will be our depth first search. A, S, G, F, H, E, C, D, B. Now let's move on to the pseudocode.
Looks like. So first we'll declare a function called depth first search. It will take an adjacency list and a start index, where start index is basically from where we are going to start, and adjacency list is a map with the starting character and linked list. You all must know before coming to this portion. So we make a list which has elements to the length of agency list, and we mark all of them as false. Then we make a stack and we put the first node into the stack. After that, we mark the stack, the visited for the position of stack. As I told you, we were keeping an array of visited to see that we don't traverse the same node again and again, as it may result in a cycle. Now we make a while loop until the stack gets empty. Then we pop out the element from the stack and then we print it. After that, we make another loop which ranges from the adjacency list vertex, like the node that we got out of the stack. We put it into the adjacency list and see all the neighbors for that node. And now if we check if it has been visited, then if it has not been visited, then we append it to the list and mark it as true. First search looks like in Python. So first we'll be declaring a function. It will take the same two arguments, the adjacency list map and the starting node. We make an array of visited and mark all the elements as false as done before. Now we make a queue. So this is the different part from the depth first search, as we are going to use a queue here, because queue implies first in first out. As we have discussed before, we want the element that entered first, the node that element entered first, to be checked out first, apart from rather than what happened in depth first search, which was using a stack. Means what came for later had to be checked out first. And so now we mark the visited as true for the starting node, and we loop over the queue until it is empty. We pop the first element out and we print it. Now we check for each element in the adjacency list of the vertex. If it is false, then we append it and mark it true. And now we are done with the breadth first search.